So here are two different antiderivatives of products of powers of trig functions that we want to deal with. And the question is, at some point we'd like to either make a substitution that will make our life easier, or if we must, as a method of last resort, integrate by parts to try to make our life easier. But if we can get away with just doing it with a substitution, that's probably the best, right? Because substitution is our friend. So let's start on the left-hand side. Is there a substitution we can make on the left that can bail us out? Keeping in mind, by the way, that when we say sine cubed of x, what do we really mean?
Sine squared x times sine of x.
Well, that's true. It's sine squared of x times sine of x, but just to the point I wanted to make about it is that it's the sine of x, the quantity cubed. And so putting that quantity around it and a cube on the outside makes it look like an inside function, right? An inside function that we would like to use substitution for. So does it work? What substitution can we try here that might have the benefit of making our problem immediate, sir?
Well, you visualize that as sine squared x times sine of x, and then instead of sine squared x, you do 1 minus cosine squared x.
Okay, sure. So let's defer this u substitution for a second, and let's follow this suggestion. Instead of seeing it as 3 powers of sine, let's take one of those powers and peel it off to be out in the front. So instead of sine cubed, we'll make it sine squared times sine of x. So that's what I like to call peeling off a power. And by peeling off that power, what we'll find out is that we can make a substitution and use that power of sine that we peeled off to be part of our du. So what we're shooting at here is that we would like our du to be sine of x dx, or to look like sine of x dx. But if that's what we're doing, if that's what I'm trying to make part of my du, then what am I making part of my u? If du is proportional to sine of x, then what is u? Cosine. So we're buttering ourselves up here for the substitution u equals cosine x. But we can't really get away with that substitution. Du would be minus the sine of x dx. We can't get away with that yet, because we haven't explicitly said how the rest of this integral depends on cosine of x. Because we have a cosine of x piece in here that we know how to turn into u, but then we have this sine squared piece that we wouldn't immediately know how to turn into a u. But, Sarah, what did you say a moment ago we could do with that?
Change it to 1 minus cosine squared x.
Right, so here comes the Pythagorean identity to the rescue, once again. It's really good at rescuing things. Is that, according to the Pythagorean identity, sine squared of x is equal to 1 minus cosine squared of x. 1 minus cosine squared. And so I can use that to turn my integrand into 1 minus cosine squared x times out in the front to cosine of x. And then I have sine of x dx out in the front, sine x dx. And I'm integrating that with respect to x. But now, what have we gained? We've gained the fact that we can express everything in terms of u and du. So out in the front, cosine of x turns into just u. So this becomes the integral of u. What does 1 minus cosine squared of x turn into? 1 minus u squared. And then sine of x dx. Yeah, we would have to turn that minus sign to the other side. So this is minus du in my integral. And now I have an integral which is no longer trigonometry at all, but it's just powers of u. That's great news, because antiderivatives of powers are a whole heck of a lot easier than antiderivatives of trig functions, powers of trig functions especially. So now our substitution has given us something we can work with. Questions on getting to here? because this was the tricky part. Yeah.
The negative, I just don't know that.
Oh yeah, let's rewind for a second and talk about that negative. All right, so big finish. So this is going to be minus, what's the antiderivative of u times 1 minus u squared? Yeah, let's make it u minus u cubed. So this antiderivative is 1/2 u squared minus 1/4 u to the 4th. And that was the calculus. Now all we have to do is resubstitute, right? Don't leave those u's in there. Switch from u's back to x's to find out that our antiderivative, all told, is minus the quantity 1/2 u squared, and since u was cosine of x, that's cosine squared x, minus 1/4 cosine to the 4th of x. Space here. Plus c. And there you have it. So the first technique we used here was a technique of taking sine cubed and peeling off one of its powers. And then once we peel off that power of sine of x, that sets us up to make a substitution for cosine. U equals cosine x. And then du is minus sine of x dx. So just to make everything line up here. That sine of x dx in our original integral becomes the opposite of du. So how, thinking strategically, how would we have known that this method will work? So what made this an option for us? What was true about the powers on cosine and sine here? They were both odd. In particular, the one that we peeled off started odd, right? So we started with this odd power of sine of x, and that allowed us to peel it off. When I peel off a sine of x, I'm left here with an even number of sines left over, right? After all, when you subtract 1 from an odd number, you get an even number. And as soon as we have an even number of powers of sine or an even number of powers of cosine, that allows us to use the Pythagorean identity. Because we can trade out an even number of sines for an even number of cosines. Because sine squared is 1 minus cosine squared. So with that in mind, here's a question. Suppose that instead of cube, we started with, I don't know, 5th power. And also, let's suppose that maybe there's some power on the cosines as well. What would be different?
You could use cosine to the 4th.
So cosine to the 4th is still going to be out front here.
Because it's even.
Yeah, leave that by itself because it's even.
Some substitution would be easier to see that that's something we should do.
Well, yeah, again, substitution is going to make it nice, except what's the problem with this is we can't substitute in the beginning. Because sine of x quantity to the 5th, okay, we could substitute u equals sine of x, but then the problem is du would only account for 1 power of cosine, and we have 4 of them to account for here. So that's why an immediate substitution is not enough. Actually, ironically, an immediate substitution would have worked on the example we did just previous to this. But in this one, it will not. So we have to use this peel off a power method. Because we have an odd number of powers of sine, let's do what we did before and peel one of them off to become part of our du. Right? And if I peel off 1 power of sine, how many powers do I leave left over? I leave 4 of them in this case. And again, that power that we peeled off, we're setting up to be part of our du. And if we're setting that up to be part of our du, that must mean that we're thinking to substitute u equals cosine x. So that du is minus sine of x dx. And again, that forces me to account for there being a minus sign up in this part of the du. Okay, But again, we're faced with this question of how do we express everything on the left of my du here? How do I express it in terms of just cosine? Well, cosine to the fourth is already in terms of cosine. So sine to the fourth we need to put in terms of cosine somehow. Well, how do we do that? How did this, I claim that this unlocks the Pythagorean identity, but how does sine to the fourth have to do with the Pythagorean identity? What's a better way to write sine to the fourth? Sine squared, squared. Exactly. Or sine squared times sine squared. Either way. Right. Right. So instead I'm going to write this as sine squared of x, the quantity, squared. And now the Pythagorean identity lets us trade out the sine squared. Minus du here. Whatever. Cosine to the fourth out in front. But sine squared is 1 minus cosine squared. So we can replace the sine squared, just the same way we did before. And now our entire integrand is in terms of u, namely u to the fourth times 1 minus u squared, quantity squared, times minus du. And now this is just a polynomial again. In order to integrate it, we would have to expand out all the powers of 1 minus u squared, quantity squared. We would have to just expand that out with algebra. But from here on, the rest is gravy. I'm just going to say done for now, okay? Rather than go through the rest of those steps. Because making the trig substitution to get to that stage is the tricky part.